Hi, good afternoon, everybody. My name is Saurav. I'll be talking about motion planning for active data association and localization in non-Gaussian belief spaces, right? So let me start with a big picture overview of what we're talking about. So we're interested in the problem of global localization. So Ryan McDonald, you might be interested in this. It tries to answer the question, where am I in the world, right? And in this problem, the robot is placed in an arbitrary location, and it's not given any prior information about its pose. So it doesn't know where it starts. It's put randomly somewhere in the environment. The robot has a map of the world. So to localize, it tries to associate what it sees to its knowledge of the map. But in the real world, maps can have ambiguities, right? So if the robot sees a red trash can, there could be a data association problem. Does the robot see a red trash can in Ben's office or Jerry's office, right? So it's confused. So the question we ask is, can the robot take some actions to confirm its true pose, right? This process is called disambiguation. So what is belief space? We come to belief space planning because systems have uncertainty, and in our case, we have sensing and motion uncertainty. So we need a probabilistic representation of state, which is called the belief state. And a belief state is simply a probability density function over the possible physical configurations, and a Gaussian belief distribution is quite commonly used. And the belief space is where the belief state lives. So Gaussian belief space planning is relatively simpler. So in this example, the robot sees is in a world with 3 doors, different colors. So if it sees the blue door, it has a high likelihood of being here. So you have a nice unimodal distribution. But what if a unimodal distribution doesn't work well to represent the belief? So what if I put it in a world with 3 blue doors? It sees the blue door on the left corner, right? And it has a data association ambiguity. It doesn't know which blue door it's looking at. So it's confused, right? So there's a multimodal hypothesis, and each hypothesis is equally likely because it doesn't know where it started. So the challenge is that we have ambiguous data associations in the real world, which can lead to a multimodal belief. And it happens quite often in real life, which means that, and it's quite common in environments with symmetry, like office environments. And belief modes in a multimodal hypothesis could be widely separated by obstacles. So it's hard to plan. You cannot base your actions on one pose of the robot, right? And finding the shortest relocalizing plan has been shown to be NP hard. So, and if you think about it, an action that is good for one hypothesis may not be good for another, right? So the goal for us is to generate an algorithm that allows the robot to relocalize in finite time. So relevant prior work. So Fox, Burgard, and Thrin, they showed that the intuitive, just randomly moving around until you figure out where you are, doesn't work. Especially in symmetric environment, it's not really useful. So their approach was to generate random targets in the vicinity by atomic actions and pick the best one. Dudek, Romanek, and Whitesides were the ones who showed that the problem is NP hard to find the shortest relocalizing path, right? And Jason O'Kane and Laval were the ones who showed that in symmetric environments, for robots with perfect odometry, no sequence of observations can disambiguate in a symmetric configurations, right? So what do we give? What are our contributions? So we provide a multimodal motion planner, abbreviated M3P. So in our case, we don't have orientation sensing. We take an information theoretic approach to target selection. So for each hypothesis, we choose a target where it should go. And we disambiguate in finite time, and we provide guarantees for the case of full disambiguation. We also show an experimental demonstration. In the experimental demonstration, we trigger convergence to a unimodal belief when our confidence in that belief is 99% or more. State of the art would converge at 80%, so in this case, higher is better. So assumptions, the map is static, the robot operates, the map is given also, and the robot operates in a static world. And there is some uniquely identifiable information to confirm the true hypothesis, right? This could be some visual feature with a distinctive appearance, some geometric shape. And this is a necessary condition for full disambiguation. So what is our method? So we take a 2-step approach. In the offline phase, we generate what we call a uniqueness graph by sampling states and uniformly. And this provides us targets to visit. And in the online phase, we pick a target to go for each hypothesis, generate actions, pick the best action, and execute this in a receding horizon manner. So what is this uniqueness graph? So a uniqueness graph is basically relating the similarity of observations at 2 points in space. So in this example, you have features which are colored stars, for example. So node V alpha is sampled, it sees gray and red. V beta sees gray, red, and blue. So there is an edge alpha beta with weight 2 because they both see gray and red. Between beta and gamma, there is an edge with weight 1 because they both see only a blue feature. But between alpha and gamma, there is no similarity in the observation. They don't see anything similar. So digging a little deeper, the edge weight omega alpha beta is provided by the function tau, which acts on the observations at those two states, right? And what tau is a distance metric in observation space. So the uniqueness graph concept is agnostic to the observation model. Works with features, could work with raw data, raw measurements, and it only requires a notion of distance in observation space. And the complexity of constructing this is O(n) squared because you check every node with every other for similarity in the information overlap. So how do we represent the belief? We take a mixture of Gaussian's approach to representing the belief, which is basically a linear, weighted sum of Gaussian densities. So in the online phase, what we do is, for each hypothesis in the belief, right, we pick a target. Then we create a candidate policy to guide that belief, that hypothesis to its target. So we get a set of policies, right? And then we pick the best candidate and execute it for some t steps. T is the horizon. And if a hypothesis is eliminated or a constraint violation is foreseen, I'll stop and replan. So let me explain each step in detail. So how do we pick a target? So for each mode, we get the neighboring nodes from the uniqueness graph. And then we find the target, which has the smallest outgoing sum of edge weights to the neighborhood of other nodes. A lot of words. Mi and mj are two nodes, are two hypotheses. You get neighborhoods ni and j, and they contains node v1, v2, v3, v4 from the uniqueness graph. So in this example, let's say v2, v3 have an edge, and v1, v3 have an edge, and v2, v3 has a thicker edge, which is basically the similarity of information is higher. So what happens is mi wants to go to v1, and mj wants to go to v4. So how do we generate the candidate policy? For each belief mode, we use RRT star to, once we found the target, to create a trajectory. And then over that trajectory, we construct a local feedback controller. So to pick the best policy, we need to compute the information gain for each policy, right? So for each belief, we assume that the robot is at that belief. And we execute that policy and propagate all the modes. And we compute the information gain, which is a function of the number of hypotheses reductions and factors in the cost of collision. And we compute the weighted information gain and pick the best policy with the maximum weighted information gain. So we did some real-world experiments. So our challenge was that we took a low-cost, we built a robot ourselves, basically fits on the palm of your hand. It's equipped with the monocular camera as the only exteroceptive sensing. The map is known a priori. And the map is basically a maze with duplicate-looking rooms. And we achieved that by putting similar-looking landmarks in the rooms. And the goal is to recover the true position of the robot, right? So let me explain this to you with a video. So what is happening is that you have this maze with identical rooms, R1 to R8. And you have this narrow passage in the middle, which has some unique landmarks here. So and here's what the robot sees. This is a top view. And you have these initial hypotheses, which are generated by gridding, and then taking stationary observations and eliminating the unlikely hypotheses till you converge to the fixed set. So now you see the candidate actions are being planned for each hypothesis, and they all want to go here, right, into this narrow passage. But the robot started here where the blue circle is. So you see the actual robot is turning, and once it turns, what's going to happen is it's going to see something on the outside wall, right there. Right. So that leads to a disambiguation. This hypothesis gets deleted, so triggers replanning, right? Again, it's figuring out the candidate action for each hypothesis, and again, there was a disambiguation. So finally, what happens is you get left with two hypotheses, and you see there's like the sensing uncertainty. The markers are blinking, so that's like detection, non-detection. So now the robot started here, but what's happening is that the candidate policy based on this hypothesis was chosen. So this is interesting, because what is happening is that due to the symmetry, the robot is able to come out of the room. So once it gets close to the door of the room, it tries to replan because it thought it might get close to collision. Remember, there's only a camera for sensing. And as it's moving, it's stopping and taking these little turns to exploit locally the information that is available. And you can see the robot here making small turning motions. And what it's doing now is it's trying to go into the narrow passage. So again, it replanned. And the robot should turn the corner any moment and see what is inside. And inside, we have a unique landmark, something which is distinctive, which can help the robot confirm where it really is. And all the time, it thinks that this is a better action to take based on this hypothesis rather than where it actually started. Don't collide, don't collide. OK, yeah. So here. So the unique landmark observed, you came down, converged to the true hypothesis. So conclusions. M3P sequentially disambiguates a multimodal hypothesis through active data association. We can generate actions even when the belief modes are widely separated by obstacles. In this domain of problem, trajectory optimization-based methods are hard to use because it's difficult to generate an initial guess. We provide a non-heuristic approach to target selection. So instead of taking random targets in the vicinity, we actually come up with a way to choose targets wisely. And then we are conservative in accepting the true hypothesis. We can, 1 minute left. So, okay. So quickly, applications. We can recover from global failure or kidnapped robot scenarios. We think it's an interesting application is SLAM, loop closure. So if you have data association ambiguity in the loop closure, you might want to use something like this to have to disambiguate the loop closure. Happens to the best of us. Dirty laundry. Experimental evaluation is limited to the lab scenario. Complexity of online replanning might be limited for a large number of initial hypotheses. Belief update does not consider PDF truncation due to obstacles. So what this means is that passing through a narrow passage is informative because the belief really, the PDF should get truncated. And we want to expand to experiments or scenarios where the belief splits during the disambiguation process. So each hypothesis might split into child hypotheses. Questions?
Thank you. Nick. You have to be loud.
Okay, no problem. I can be very loud. So first question is, we have this weighting function that you're using to build the uniqueness graph, which is essentially how dissimilar this node is from the other nodes given hypotheses. But then you actually evaluate the path based on mutual information or information gain. Why not use mutual information in place of that weighting function? That's one question. And the other is, it looks like you're relying very heavily on local sensing to keep you out of trouble if you guess the wrong mode. Do you have a plan for addressing the case where, like, if you genuinely don't know where you are, there's a series of hits that you could fall into and never realize until you actually know where you are?
Okay, so let me rephrase the first question. The first question was that we are taking a notion of dissimilarity of observation in the environment, and why aren't we using that directly?
No, the other way around. Use mutual information, which is what you use for the optimization in place of the similarity function.
Okay, so I don't think I got. Okay, based on my understanding of that question. So the way we are using it is think of it intuitively, right? I don't know where I am, right? Let's say I'm in a grid world, Manhattan City, no street signs. All the streets look similar. How do I figure out where I am? I know that there is some building with a red flag on top, so I want to go see that. So it's based on, like, if I'm in street 1, I'll take action 1. If I'm in street 2, I'll take action 2. So based on this intuition, we select targets. But how do we select targets? We want to select targets where I can go and see something dissimilar to what other hypotheses have in their vicinity, right? So that's the underlying concept. So once we've chosen the target, then we just want to guide that belief, that hypothesis along some trajectory to that target. And the approach is greedy, right? This is more like a get out of jail card. What I want to do is, in some infinite time, get rid of the incorrect hypothesis. As to your second question, yes, we're using local sensing. So what if the robot was to get stuck in a pit, for example, and I think to answer that question, it relies on the modality of your sensors, right? Of your local sensing. So, for example, if I enter into a room and the room gets closed, right, and that room looks similar to a lot of other rooms, I have to realize that since I cannot get out of this room, I cannot get rid of the wrong hypotheses. So, and that is kind of inbuilt. So implicitly, M3P will just try to get rid of hypotheses sequentially, and if we can't, then I guess the next step is to actually recognize that we can't get rid of more hypotheses and stop.
Any more questions?
Sort of. This approach is a greedy approach. The T horizon we chose was 600 time step, so that's 60 seconds with a 0.1 second time step. Even if you chose a really long or really short horizon, this would still work. I mean, you would still get disambiguations in finite time. It's just that if you had short horizons, you'd spend a lot more time doing replanning. You'd have to trigger replanning quite often. The longer the horizon, the more risk you are at of, in our case, bumping into something. But that's kind of taken care of by the fact that as soon as there is a disambiguation, you trigger replanning anyway. So I don't think that the
But if that's the case, then if you just follow the greedy mutual information, we might recover eventually. Just following the best information gain, and then we might recover after some time.
what do you mean by like just best information in terms of like the best policy here?
Call it distance, some dissimilarity. But if it's live divergence, which is mutual information, if you just follow greedy information gain, then we might just recover.
But the problem is that you don't know where you are. So you don't know where you are, right? So you have multiple hypotheses, and for each hypothesis, you think this is where you could go and get some distinctive information. It might be that in the uniqueness graph, you don't have any nodes in your vicinity that have zero overlap. You might have nodes that always have some overlap to the vicinity of neighborhood of other nodes. So you do need to reason about the propagation for all the beliefs. I don't think. Yes, what you're saying. Given enough time, it would work too. So I don't think.
Okay.
But anyway.
We'll sneak in one more question right here. And then
Yeah, so if you look at the similarity graph or the uncertainty graph,
Uniqueness, yeah.
uniqueness graph. So if you take the same landmark, and if you look at it in different lighting conditions and images, for example, it could look quite different.
Absolutely.
Or if you could also look at it through multiple sensors, it could look quite different.
Mm-hmm.
So have you any intuition about how best to deal with all that?
Absolutely. So yeah, that's a really good question. We cheated. We used fiducial markers, which you can detect the appearance, and we got rid of the. The focus of this paper wasn't to look at the perception, but yes. So the second part of your question is kind of depends on the robot that you start with, right? So what's a sensor modality? For the first part, you have to then the weight of the edge becomes probabilistic itself, right? So when you're building the uniqueness graph based on your perspective, right? So you might have some knowledge of the world. Let's say the lighting condition affects the appearance of a landmark. I built the map at 5 p.m., right? But I want to operate at 9 p.m. where the lighting is different, the perception will be different. So I have to make a probabilistic weighting function. If it looks completely different, I guess. So while building the map or during online.
It seems to me like you have to go reacquire even your primary uniqueness graph.
I'm gonna actually now interrupt and say that you guys should talk about this later on, and we should thank the speaker so we can keep going. So thank you.